A very great pleasure to welcome our third speaker this afternoon, Alexei Skorobogatov, who will tell us about the timeless attraction of diagonal quartic surfaces.
Thank you very much, Sarah. So in this talk, we look at diagonal surfaces, mostly of degree 4, but not necessarily. And this is motivated by Peter's interest to these objects, which of course belong to a very classical tradition in number theory. So in some way, we can think of diagonal equations as the case when variables separate. So this is like differential equations when separating variables allows us to solve them explicitly. So something similar happens to diagonal equations in number theory. And the case when degree is 4 gives us an example of a K-free surface. So maybe this is the most famous type of K-free surface. In this case, the Picard group, which for K-free surfaces and also for diagonal surfaces is equal to the Néron-Severi group, is isomorphic to free abelian group of rank 20 over an algebraically closed field. So this has complex multiplication by square root of -1. And let me quote from Peter's paper: we are interested in K-free surfaces more generally as being the simplest kind of variety whose arithmetic theory is still rudimentary. So the hope is that looking at diagonal case will allow us to do more than for the general case of K-free surfaces, so understand things a bit better. And the crucial feature is, of course, the very large automorphism group that these surfaces have. So we can multiply each coordinate by a deep root of unity. And in this way, we see that the automorphism group, algebraic closure of Q, for example, contains this group G, which we can treat as a group scheme or just as a finite abelian group. And like a classical example is André Weyl's extremely influential work from the late 40s, where he computed explicitly using character sums the action of Frobenius on what we would call cohomology, Étale cohomology, second Étale cohomology group of this surface of a finite field. Well, of course, this was before cohomology was invented. Anyway, this served André Weil as an evidence for stating the Weil conjecture. So he looked at some examples like Grassmannian varieties and flag varieties, which were sort of like easy to analyze. And this was a genuine case where non-trivial Galois representation could be stated as a particular case of Weil conjectures. And in this talk, I'm more interested in the case of number fields. So the question is, what can be said about the arithmetic of such diagonal equations, and with focus on the case of degree 4, when the ground field is a number field. So in that case, we know that an important role is played by the Brouwer group. And for schemes, the Brouwer group was defined by Grothendieck in the 60s as second Étale cohomology group of your scheme X with coefficients in GM, the sheaf given by the multiplicative group. And the question is, what is this group? So the way it appears is as follows. So let me just mention that in the case of degree 4, diagonal quartic surface of the algebraic closure of Q, this group is, I mean, it's looking deceptively simple, but this says nothing about the Galois action on it, which is, of course, of interest here. And the role of the Brouwer group is due to the Brouwer-Mannian obstruction. So the set of Q rational points on the surface can be thought of via diagonal map, a subset of the topological space of adelic points. So we look at points on our surface with coefficients in real numbers and also with coefficients in p-adic field for all primes p. And we put the product topology on this product. And so we get this topological space of adelic points. And the diagonal image of rational points is contained in what we now call the Brownian set. And the Brownian set is defined as follows. There is a pairing of adelic points on our variety X with the Brauer group of X, which goes as follows. An adelic point is a collection of local points. And if you have an element of the Brauer group, you evaluate Brauer group of X, you can evaluate this element at any point, and this gives you an element of the Brauer group of a local field. You can prove that the sum of local invariants that you get is a finite sum. That's because the variety is projective in this case. And if the sum is non-zero, then by global class field theory, you know that this collection of local points doesn't come from a rational point. So there's a way to control the image of Q points inside the adelic points. And okay, just some comments about the use of the Brauer group in this connection. So the Brauer group of the ground field plays no role here because the corresponding sum is always zero by global class field theory. So we are only interested in the kind of non-constant part of the Brauer group, that is to say, Brauer X modulo the image of the Brauer group of Q. And here there's basically there are two layers. There's the subgroup consisting of the elements of the Brauer group that go to zero under the base change from Q to Q bar, and those elements that survive. So this easier part called Brauer ones, usually referred to as algebraic Brauer group. So in our case, is calculated. So this is a Galois homology group, and it's not so hard to calculate because in this case, the Néron-Severi group, as I said, as I mentioned before, it's a finitely generated free abelian group, and if you know its base, its Z basis, then it's a task we can give to a computer to calculate this homology group. And the usual spectral sequence, which I will not write down for generality, you can imagine what it is. It's a spectral sequence of Galois homology with coefficients in a Untitled homology group of X considered over algebraic closure of Q, gives you this long exact sequence of low degree terms. So it starts with the Brauer 1 modulo Brauer group of Q, then that's the group we are interested in. And if we continue, we get the Brauer group of the algebraic closure, and we land in its Galois invariant part, and then the sequence continues like this. So let me mention the questions about, the standard questions that people mention in this connection when we talk about K-free surfaces over number fields. So let me state them in a kind of way we usually state undergraduate exams with multiple answer kind of questions. So true or false. So, okay, let's start with the most natural question, namely, if my diagonal quartic surface, or let's say any K-free surface or Q for that matter, has one rational point, is it true that it has infinitely many of them? The question is interesting because K-free surfaces are in some respect like mythical creatures. It's some sort of griffin. They possess some of the properties of elliptic curves, like a non-degenerate holomorphic form, and some of the properties of rational surfaces, like the Picard group is torsion-free. So I genuinely don't know what to expect. What kind of answer to this question we're really expecting. And well, a slight modification of this question is question 2. If a K-free surface has one Q point, our Q points are risky dance. So there are arguments in favor of this, but how convincing they are, I really don't know. And the Brouwer group, I mentioned that the Brouwer group plays an important role in the Brouwer-Mine abstraction. So true or false, is Brouwer group finite modulo the Brouwer group of the ground field? Okay, and now we want to know the structure of the Brouwer-Mine set, and what one might reasonably expect is the following description. We expect that there should exist a finite set of places which contains all the usual culprits, which are primes of bed reduction and the Archimedean primes, and hopefully nothing else, such that the primes that show up in the description of the Brouwer-Mine abstraction are precisely these primes. In other words, so this boils down to the statement that we expect that there is a open and closed subset of this finite product of spaces of local points, such that outside of this set S, we need to include all points. So this expected picture tells us that the Brouwer-Mine set is, so we partition the entire delic space into finitely many pieces, and exactly one of them, namely the one which contains the images of rational points, is the Brouwer-Mine set. So for diagonal quartics in particular, one might expect that S is this set. So we look at the primes of bed reduction, which are those dividing the coefficients, if they are integers, let's say, and also 2. Next, that's a question which extremely should be probably considered to be quite difficult. The question says, is it true that the set of rational points is a dense subset of the Brouwer-Mine set? So this takes care of the Hasse principle and what we call weak approximation. In a few moments, I'll say what evidence we have for I mean, whether we can reasonably hope to have to expect that this question has a positive answer. And my last question is, in analogy with elliptic curves, I mentioned that diagonal quartics have complex multiplication by square root of -1. In this case, an elliptic curve would be expected, I mean, it's known to have potentially good reduction. Does the same hold for K-free surfaces? So in particular, diagonal quartics, do they have potential good reduction at the prime 2? To the best of my knowledge, this is not known. I mean, this question looks completely elementary, but I'll be really pleased if maybe one of you could tell me that this is true and explain why. Okay, now in this second section of the talk, I would like to give a review of Peter Swinnerton-Dyer's work on diagonal quartics. So he was attracted to this equation and wrote no less than 7 papers about diagonal quartics. And his earliest work is published in Journal of London Math Society in 1943. So it was submitted in 1942 when he was 15 and still at Eton. So he was reading books about number theory and history of number theory, and he came, I mean, my understanding is that he found out about Euler's parametric solution to this equation, and he deduced the solution himself, and probably this is how this paper appeared. And then he returned to this 20 years later, 25 years later. I think this this paper is quite nice. It's a nice and very clear proof of the following result. So let's call this surface X. It visibly has rational points, and Peter proved that the set of rational points is a dense subset of the set of real points, of the topological space of real points. And the proof is quite nice. This surface has many straight lines. It contains many copies of projective line. So if you I mean, just by, for example, look at the line given by the condition A equals C, B equals D. I mean, that's a P1. If you take this line and you consider planes through this line, then residual intersection, so intersecting a plane through this line with your quartic, will be this line, of course, plus a cubic curve. So in this way, you get a pencil of curves of genus 1. So that's an elliptic pencil I mentioned here. But this surface also contains other lines which are skewed to the line we started with. So one of those lines gives a section of this pencil which turns fibers into elliptic curves, not merely just curves of genus 1, but genuine elliptic curves with a point, with a rational point. But then you can find yet another line which gives rise to a section of this pencil. And what Peter does, he shows that this section has infinite order, and then it's easy to check that the set of real points in each fiber is connected, and so you get immediately that if your fiber is a smooth curve, then the set of rational points is dense in a set of real points, and then that's it. That's basically the proof. So that has an important ideas, which Peter kept revisiting all his life. So, well, the next paper is a different nature, and it's written jointly with Richard Pinch, and this was based on André Weyl's work, which I mentioned before. So Peter wrote the L function, I mean, the explicit expression for the L function attached the Galois representation on the second Untitled homology group, and he was going into the familiar direction of Burgess-Nye conjecture, and he was looking for, he wanted to get an explicit analytic expression for the value of this function at the point 2. So he wrote this, and I guess the progress in this direction was hindered by the fact that the corresponding conjecture, maybe the block cutter conjecture, I mean, we don't know how to calculate these terms explicitly. So Peter has expression for them, and he would want to interpret this expression in terms of some important conjecture, but he failed to do so because we don't know these numbers, so we don't know how to interpret like the rational part of this number and the transcendental part of this number. So yeah, let me continue. The next paper about diagonal quartic surfaces is a very complicated paper which goes in a different direction. So in that paper, Peter was interested in the Hussey principle with the Brownian obstruction. And the result is conditional modulo 2 difficult conjectures, one of which is an extremely difficult Schinzel's hypothesis H, which so the far-reaching generalization of Budnikovsky's conjecture and the twin prime conjecture, which states that irreducible polynomials in one variable with integer coefficients represent primes if some obvious necessary conditions are satisfied. And the other conjecture which his method requires is the finiteness of the Tate-Shafarevich group of elliptic curves. So the starting point of this paper was the following observation. If you have a diagonal quartic surface such that the product of the coefficients is a square, then this surface has two transversal pencils of curves of genus 1. So the way to see this is as follows. Look at the diagonal quartic equation, and then squaring each coordinate gives a morphism to a diagonal quadric surface. And if the product of coefficients is a square, then the quadric has two pencils of lines on it. And the inverse images of these lines on the quadric give you curves of genus 1 on the diagonal quartic. So that's the construction which Peter liked a lot and was revisiting again and again. So and what he did in this paper, he looked at such a pencil of curves genus 1, And one can see quickly that fibers of this pencil are genus 1 curves, which are two coverings of their Jacobians. So, and then you try to do two descent in a family, and he required some technical conditions which are referred to as condition D, which are some sort of like general position condition in the arithmetic context. And this was this was a paper which is connected to much related work, but in this talk I will only briefly mention this direction. Okay, and then later Peter sort of looked at diagonal quartics from a different perspective. So consider this particular kind of diagonal quartic equation where two coefficients equal to 1 and two other coefficients are equal, let's say some integers c. And then again, because the product of four coefficients is a square, this surface has two pencils of genus 1 curves. And what Peter managed to show somehow, which continues his earlier work in 1969, he showed that for some values of c, like 2 or 4, the set of rational points is actually dense in two-adic points and also in the product of the space of two-adic points and real points. So you can view this as a step towards weak approximation. Well, of course, we are approximating only at two places, but this is better than nothing. So before, only results about real numbers have been available. And this is based on Mazur's theorem that says that the order of torsion point on elliptic curve of rational numbers is at most 12. So what Peter did is he constructed a Zariski closed subset of the surface, so the union of curves, finite many curves, with the property that if one finds a Q rational points outside of the Zariski set, then one can show that the Zariski points are dense. I mean, this is quite messy because he did these things completely explicitly, and that's the reason why this work wasn't, I mean, didn't have like much development, because there's surely room for more results in the same direction, but it's not an attractive perspective somehow. Okay, there's one more paper where Peter wanted to attack, I mean, to get some numerical evidence for the block cutter conjecture by calculating interesting values of the L function associated to the middle cohomology, to the Galois representation in the middle cohomology group of high-dimensional diagonal hypersurfaces. And once again, somehow, he was asking the experts for an explicit form of expected value of these L functions at these points. And people are telling him that these things exist in the literature, but somehow the bridge seems to be lacking between the general statement of these conjectures and what one needs for concrete calculations, like in this case. And his last paper, I mean, his very last paper that was published in 2016, is about the same kind of diagonal quartic surface as I just mentioned. And because available methods for constructing rational points on such surfaces all depend on either rational curves or curves of genus 1, elliptic curves, where we can have infinitely many points. So when we want to prove density of rational points or prove that there are infinitely many rational points, so what else can one use apart from rational curves or elliptic curves? So he was trying to determine how many such curves can be found on these surfaces, but he was looking only at non-singular curves. And so he determined there are only finitely many degrees are possible for genus 1 curves, and for, you know, and only lines are the available rational curves. I mean, if you assume that they're smooth. So Peter mentioned to me once that something like, my first paper was on diagonal quartics and my last paper will be on diagonal surfaces. So he was really attracted to this maybe crucial, like a testing like case of arithmetic beyond abelian varieties and beyond geometrically rational surfaces, where he also worked. Okay, and let me just mention some related work. So question 5 is a question about the density of the set of rational points in the Brauer-Manin set, which is a subset of the space of adelic points on X. So I don't have time to go into any details. Let me just mention that there is a lot of related work that people used Peter's method, which to this date, as far as I know, remains the only available method to prove such results. And if you don't like the fact that this uses Schinzel's hypothesis H, let me tell you that hypothesis H is not needed in the case where you work on rational points on Kumis surfaces, in which case you only use the conjecture that the H group is finite, which is probably a natural thing to do in this context. Okay, so there's a lot of research going on in this, but let me also just share my experience with using this method. It's not an easy method to use. So Peter was quite proud when he could produce a very complicated solution to a difficult problem, and he didn't feel obliged to find a simple solution somehow. And next, so questions 1 and 2 are questions about the size of the set of rational points and whether or not they're Zariski dense. So that's, I mean, you could think this is an easy question, but these are also quite hard. And so this work of Peter, published in Algebra Theory, is related to earlier work of Logan, McKinnon, and van Looy, and also to work of Panikok. Okay, now in the direction, we're slightly moving towards the Brouwer groups, and things get easier when you sort of shift the focus from rational points to the determination of the Brouwer group. For example, question 3, which is a question about whether or not the Brouwer group of X is finite modulo the Brouwer group of the ground field, has a positive answer for K-free surfaces, and this is work by Yuri Rizarch and myself, and also for surfaces dominated by products of curves. So this is true also for diagonal surfaces. And finally, the question about the structure of the Brauer-Manin set also has a positive answer. So after the initial work of Colette Lehn and myself, a recent exciting work of Martin Bright and Rachel Newton on the subject has provided a completely new approach to this. And a very nice example constructed recently by Margherita Pagano shows that the answer to question 4 is yes, if 2 is added to the list of bed places. Whether or not 2 is a prime of bed reduction, it has to be added to S. So, so in particular for diagonal quartics of a Q, we now have a complete answer to this question. Okay, now in the rest of this talk, I will concentrate on the question of calculating the Brouwer group for diagonal quartic surfaces, and more generally for more general diagonal surfaces. So Peter was interested in this, and when Martin Bright was his PhD student, he was given the task of calculating the algebraic Brouwer group of diagonal quartics. So this can be done because the Néron-Severi group of a Q-bar is generated by the classes of lines. So there are 48 obvious lines on a diagonal quartic that are defined of a Q-bar. And by just looking at the Galois X on these lines, you can compute the the algebraic Brouwer group. At this moment, let me somehow make a remark that depending on where you want to, depending on what you want, there are two possible strategies in this direction. One strategy is to calculate the Brouwer group together with some sort of explicit representation of its elements, because this is what you finally will need if you want to use these elements to calculate the Brouwer-Manin obstruction. So that's one direction. So Peter was interested in this question, and he was also interested, for example, in the work of my former student, Evis Hieronymo, who produced some explicit classes which are afforded 4 or for the, you know, like for the power of 2. And this was the first result beyond the algebraic part of Brouwer group. So Peter was trying to understand what is going on, but it was like a bit complicated. And it turned out that it's easier to do this if you only look. So 2 is the most difficult prime in this connection, because 2 is a prime of bed reduction, and you know, I mean, somehow 2 is the hardest prime. I mean, maybe not just in this context. So if you ask the question about the L primary torsion, where L is a prime not equal to 2, then it's easy to answer. So this has been done in my joint work with Evis Hieronymo, and we use the fact that there's a degree 16 isogeny from a diagonal quartic to a certain Kuma surface where things can be more controllable. And this does produce some sort of Brouwer classes somewhere. I mean, let me know, go into this direction. But if your strategy is just to calculate the Brouwer group as an abelian group, if you abandon the hope of constructing the Brouwer classes, then you can go much further, because you can use cohomological methods, you can use topology. And this has been done in a recent joint paper with Damian Gwirtz, which I would like to describe. And I think it's important because the progress has been achieved by using like algebraic topology. So, I mean, nothing to do with number theories, essentially. So, so there are 3 ingredients to this method, and 2 of them are extremely well known. So first of all, the Hodge structure on the middle cohomology group of diagonal hypersurfaces is quite well known by the work of Shioda, for example. But the reason this is the reason why this is possible, we can compute this, is the work by Griffiths, which says that, which allows one to determine the Hodge filtration on a second cohomology group of a diagonal surface. I mean, of course, it's more general. This applies to any diagonal hypersurface in the projective space. The second ingredient is the work by Andre Weil, which I mentioned before, who used exponential sums, the character sums, to compute the Galois representation in the middle cohomology group. But we also need a much less known fact from topology. And this is work by Frédéric Fahm, who did the following thing. So this is quite well known to people who work on singularity theory. So you can find this in some books by Arnold and in connection with Picardo-Lefschetz theory. So what he did in down-to-earth terms is to compute an integral basis of second cohomology group. So this works for any, for diagonal surfaces or hypersurfaces of any degree, and then you need to consider the middle homology group, sorry. And this basis comes equipped with explicit description of the intersection product, which you have in the middle cohomology. So this has been used, but I think this deserves to be better known. So some of these ingredients have been used in work by Nicholas Katz, Shioda, Ulmer, and Degtyarev, Shimada, Luyenga, and more recent people who followed their work. So I would like to describe this topological ingredient because I think it's very easy. It's quite elementary and it's extremely useful. So what this allows one to achieve, so by just sheer combination of these three sources gives the following. So now we have everything we ever wanted to know about second cohomology. We can determine the integral Hodge structure, and by Lefschetz 1-1 theorem, this gives us the Nernst-Severi lattice as an abelian group together with the intersection product. The orthogonal complement with respect to this product, the orthogonal complement to the Nernst-Severi is the so-called transcendental lattice, denoted here by T of X. And I'll explain in a moment why this is important in connection with the Brouwer group. Now, by Andrew-Wade, we know that we know how the Galois group acts. So, I mean, there's a slight difficulty here, is that the Galois group that commutes with. So, let me remind you that G is this group which multiplies each coordinate by a root of unity. So this is it's an abelian group. This is just a product of three copies of the cyclic group of order D. And the action of G commutes with the Galois group, provided we work over the cyclotomic field. And then if we tensor a cohomology group with the cyclotomic field, we can diagonalize the Galois representation because we can diagonalize the action of G, and the two things commute. The two actions commute, so we get this beautiful picture. We get a vector space, which is a direct sum of one-dimensional representations given by characters, and we can determine these characters explicitly. And the reason why the transcendental lattice is of interest in connection with the Brouwer group is that we have this canonical isomorphism. Of course, the transcendental lattice is of transcendental nature, so it doesn't carry any Galois action. But if you look at the home from this free finitely generated abelian group to Q mod Z, this group does have Galois action. So this is naturally a Galois module. And the structure of this Galois module can now be determined by just combining the first 2 points here. So the first two items. So we know T as a lattice, and we have explicit bases. We can do everything with respect to our bases, and so we can determine the Galois action here. So this kind of demystifies the Galois structure, the Galois action on the geometric Brouwer group, which is a good thing, I think. And finally, it's not so hard to write an explicit two-term complex of Galois modules whose Galois hypercohomology group is the group we're interested in. So we don't need to limit ourselves to the isolated calculation of this Galois module given by the Brouwer group of X of a Q bar, then taking the Galois invariant part of this, and then looking at the algebraic Brouwer group and wonder how the two parts of the group are united in one, are united together in the Brouwer group. We can just directly calculate this Galois hypercohomology and just read off the result we need. So that's the final result. We'll get information about this finite abelian group if we follow this program. And just a slight caveat is that maybe we're just too lazy, but in this work, we restrict ourselves to the case where the cyclotomic field is a quadratic extension of Q. So that, of course, is okay if D is 4, but it's extremely restrictive in general. So we can only treat, maybe the case of D equals 6. And so one needs to understand how the full Galois group acts on these objects. But for the case of degree 4, we can get away with simply using the action of complex conjugation, which is given to us by topology. So as you will see, these bases that are referred to of the integral homology group is completely explicit. So we know how complex conjugation acts on it. And that's enough to reconstruct the full Galois action in the case when D is 4. So the farm's construction goes as follows. I want to give you, because I think it's kind of beautiful and extremely explicit. So let's start with fixing a primitive root of unity of degree 2d. So it's not degree d, but degree 2d. Then f is going to denote the Fermat surface of complex numbers of degree d. So we treat it as a complex manifold. So I remind you that G is the group which is a self-product of 3 copies of mu d. And we write its generators as u1, u2, u3 with the convention that ui multiplies the ith coordinate of my diagonal equation by zeta squared. So zeta squared is going to be, it's a primitive root of degree d. And then z is the coordinate hyperplane section. So it's a, so in my case, if d is 4, this is, I mean, for any d, this is just a smooth curve, the Fermat curve, and u is the complement. So u is the affine Fermat quartic. Sorry, it's this d is a mistake. I mean, the same would be true for any d, so I don't need to specify to the case of degree 4 here. So u is the affine Fermat quartic of degree d, which is given by equation x1 to the d plus x2 to the d plus x3 to the d equals -1. And this -1 is the reason why I need zeta. I need zeta and not the primitive root of degree d. Okay, so here's the construction of this basis in homology, which I referred to earlier. Let S be the standard two-dimensional simplex. So this is a subset of the three-dimensional real vector space, which is like this. That's the simplex we all know. So let's consider the continuous map from this two-dimensional simplex to a complex manifold given by this formula. So zeta is this root of degree 2d. That's why the image lands in U with the right-hand side -1. And that's a cell, okay? But it's not a cycle because it has non-trivial boundary. But we can eliminate this boundary by using the action of the group G as follows. So we take this cell and apply to it this element of the group ring of G. Okay, so what we do is that we multiply. Okay, U1 multiplies the first coordinate by the dth root of unity, and then the part of the boundary of this cell is the part of the boundary corresponding given by the coordinate 1 is eliminated if I apply this element of the group ring to my cell. So we get a cocycle. So this is a cocycle. And then what Frederick Farm proves, and that's essentially straightforward, that he just constructs a G equivariant deformation retract of U to the kind of geometric space of the simplicial complex generated by this cell. So we take this cell given by this explicit formula here and apply to it the elements of the group G. Oops, sorry about this. So we get a bunch of cells, and I mean they have boundaries, of course. So they have other, I mean, smaller cells on the boundary, and so together they form a simplicial complex. I mean, you can think of this as kind of sort of multi-level parking. So if all 3 coordinates are non-zero, then so if we factor by the action of group G, we go back to the plane, and in this plane we have a triangle, and above the set of interior points of the triangle there's the D to 1 map, and then this map degenerates if we look at the at the sides of this triangle. So there's a very explicit picture of this simplicial complex generated by this cell. And the crucial point is that this simplicial complex is a deformation retractor view, and you can do this in a G-equivariant fashion. And then you just write down a chain complex that represents homology of this U. And as a consequence of this, we obtain the following description of the second homology group of U with integer coefficients in terms of the group algebra of this group G. And the answer is this. This is what we get. So in terms of action of G, this is quite straightforward. And moreover, Pham determined, as I mentioned, the intersection product on this homology group as follows. So this term here is just the intersection pairing. And then he considered a form with values in the group ring given by this formula. And so when he calculated the value on this form evaluated on this cycle E, this gives in one compact form, in this closed form, it gives you all intersection products of all the basis elements. So the Z basis, which is constructed here, comes equipped with the explicit description of intersection product on H2. So how do we get from this affine open subset to the surface, to the projective surface itself? Okay, so we have the Gisin sequence. So Z is this is a curve, is a hyperplane section, and we have a Gisin map to H2 to second homology of the open set, and it continues to the second homology of X, and this last group here is isomorphic to Z, and so this last map is just the intersection pairing with a hyperplane section class. So the image of the homology of U is what they call primitive homology of X. And the point is that the kernel of the pairing, the intersection pairing of U, is precisely the image of the Gisin map. So when we mod out this pairing by its kernel, we obtain almost what we want. We obtain the intersection pairing on the primitive part of H2, and then with a little more work, we get description of intersection pairing on all of the second homology group of our surface. And of course, this is the same as second cohomology group by Poincare duality. So the rest can be given to a computer. Okay, as I mentioned, those three ingredients. So if we combine, and I mentioned how to combine them to get all the information we need about the Hodge structure and the Gauss representation on the transcendental lattice. Sorry, on the dual, like a home from transcendental lattice to Q mod Z. And then this can be reduced to calculating homology of finite groups, and the rest can be given to computers. So in our paper, we try to do as much as possible by hand, but this becomes impractical if D goes, like if D is 6, then we have to use computer. Okay, so let me kind of state the result. I mean, the result I think is less interesting than the methods. The result is just an indication of the fact that the method can be put to good use, and we can use this method to calculate what we want to calculate. But let me state the result nevertheless. It's mildly amusing. So if we consider diagonal quartic surface with rational coefficients, but over the ground field, which is the Gaussian field, so Q of square root of -1, then the two primary torsion group, the two primary torsion subgroup of the Brauer group of X is almost always algebraic. So then you have to look at Martin-Bright's tables to complete the determinant. This is quite well known. It's just one case when it's not algebraic is the case when the coefficients of the equation. So I write my equation now with rational coefficients, and the first of them is 1. So the coefficients are equal to 1, 2, and -2. But this is, of course, taking into account the usual symmetries, like And in this exceptional case, the non-algebraic part of the Brouwer group is just Z mod 2. So there's just one element. And we can also determine the Brouwer group modulo the Brouwer group of the ground field. And it turns out that this is this. So let me say why this is mildly instructive. I mean, if one would try to search for an explicit form of this Brouwer class by representing it as some sort of like quaternion algebra. So the usual strategy would be to look at the function field of this variety, take two rational functions, and consider the quaternion algebra, and then try to play with residues to make sure that this class is non-ramified. This wouldn't work because it's not possible in this situation to lift the unique element of order 2 in the image of the Brouwer group, in the geometric Brouwer group, to the Brouwer group of the ground field, because these classes, I mean, you see that you would have to somehow to capture the class of order 4, which you won't be able to do it using quaternion algebra. So this explains why this is a difficult task to find explicit Brouwer classes given by some explicit form. And just to comparison, I mean, just to tell you that now we have a complete classification of Brouwer groups of diagonal quartics with rational coefficients. Let me just mention very briefly the previous work with Hieronymo, where we looked at odd order torsion subgroup in the Brouwer group. And so basically, the elements of the Brouwer group modulo the Brouwer group of Q can only have order a power of 2, 3, or 5. And somehow then there is a complete answer in terms of coefficients. I mean, it's not so important what this answer is. The important fact is this is fully determined now. So this is the main theorem of the ground field, of the Gaussian ground field. And as a consequence, one can obtain the result of a Q. So here we have two exceptional classes. And the Brouwer group itself, I mean, the interesting part of the Brouwer group is Z mod 8. So it's even worse here. If we wanted to have our element, our non-algebraic element represented over Q, we would have to look at some sort of construction that would give us an element of order 8. So that's not something people want to attempt, I suppose, but unless they have a conceptual approach to this. And again, there is a similar result for odd torsion, just to give a complete picture. Okay, and I would like to finish with listing some of the open questions. Well, of course, it's interesting to try to explicitly determine the generators of Brouwer group in those cases and the resulting Brouwer abstraction. But my expectation is that one would need to find a roundabout way to do that, rather than trying to write these elements explicitly as some sort of cyclic algebra, some cyclic symbols, or so maybe one would be able to do it without, but I'm not sure. So this seems like a very complicated thing to do. Let me give an example of the situation in which the Brouwer-Manin set is not equal to the set of adelic points on X in complete down to earth terms. So this comes from the work with Hieronymo, and if you look at this infinite family of diagonal quartics of a Q, so n can be any integer here, then it turns out that every integer solution of this where all 4 coordinates are integers satisfies this divisibility condition, and 25 divides the product of coordinates. And the key fact is that this is not a local condition. You can find a 5-adic solution to this equation which does not have this property. So this condition is a failure of weak approximation. So it comes from the fact, it's a global fact. So it reflects the fact that in this case, there is a 5 torsion element in the Brouwer group that produces a non-trivial Brouwer-Manin abstraction. And similar examples are known for 3, but not for 2. So, and again, the reason for this is that we don't have good control of Brouwer classes, as I just explained in this case. Here's a funny question, maybe much easier to answer. I said that there are 2 exception classes in the case of ground field Q, and there's only one over Q of square root of -1. And we don't know if these 2 surfaces are isomorphic of a Q. Of course, the first thing you try is to check whether they have isomorphic Galois representations, and this is indeed the case here. So over all p-adic fields, they are isomorphic, but even integrally, when L is not 2. But we don't know what's happening over Z2. So these surfaces are kind of twists of each other. I mean, all of these diagonal surfaces are twists of each other, but those 2 I don't know. Maybe that's a fun question. I mean, if somebody knows some invariant which I can use, please let me know. And the very last question is a general question. Are there any examples, for example, of K-free surfaces where topology could be used to compute the second cohomology group, maybe the second homology group and then second cohomology group, and hence the Brouwer group in the way like I did in this talk? So there might be other cases where different topological constructions could do this, and I think it would be quite interesting to explore that. Okay, and I would like to stop now, and thank you very much for your attention.
Thank you very much for this interesting talk. Are there any questions for the speaker?
So, Alexei, as far as your last question, you must have thought about the Delsarte surfaces.
I will. I haven't done that.
So, you know, I mean, the symmetry group and the étale cohomology is the same. You don't. I don't know whether there's a kind of way of putting together the FAM description of the topology. I think the algebra should be straightforward otherwise.
Oh, thank you very much for this. Yeah.
So Schroeder followed this. Schroeder treated these in exactly the same way as the Fermat hypothesis.
Oh, that'd be cool. I mean, that'd be great. Yeah, thanks so much for this.
Are there any other questions or comments?
I have a question about the end. So in the end, what you're saying is that if you take diagonal quartic surfaces of a Q, if the coefficients are general enough, so you're showing the exceptions where the transcendental Brouwer group might be non-zero.
Yes.
In most cases, it is trivial. I mean, the whole Brouwer group is algebraic.
Yes.
Yeah. So now it's algebraic and it's computable because H1 Q plique X bar. So presumably, in most cases, that is, unless in these very specific cases, one should be able to find generators for the Brouwer group, right?
Yes, possibly.
And
yes.
Then the question is it then possible to put that on a computer and start looking whether the Brouwer-Manet abstraction is the only one?
I think Peter tried to do just this, and Martin Bright will probably able to add more information to this. But Peter did this, and he had cases where he couldn't find any rational points, and the Brouwer group is, I mean, Brouwer group could be trivial. I mean, there are many cases when Brouwer X is just the image of Brouwer Q. And he was looking at such examples, and of course, this is hindered by the fact that this is extremely hard to find rational points. I mean, the graph is extremely slow.
There is the LTS example. There was the smallest rational point, non-trivial, the height is very high.
Yeah, exactly. So I think Ronald von Leuk was looking into what kind of rate one expects for the growth of the rational points of bounded height. Is it logarithmic, or is it log, or is it log to some power, and it seems to be like there are some examples when the rational points do appear, and some other examples where you have to go extremely far to find rational points. So we don't have an efficient way of checking this, to answer your question.
So we need people from the analytic number theory to tell us that for most diagonal quartic surfaces, if they have a rational point, then the height is not too high.
Well, if you're interested in like statistics, then there is this paper by Dan Lachran, Masahiro Nakahara, and Damian Gwiertz, where they look at a different kind of diagonal K3. It's like weighted with of degrees 2, 6, 6, 6, like in weighted projective space.
Yeah.
And there they do statistics on distribution of Brouwer group. And as you say, the cases where transcendental Brouwer group appears are negligible somehow. That's true. Yeah.
Any further questions? If not, then let's thank the speaker again. And we will resume in 13 minutes with the last speaker of the day, Brian Birch.